All right, we are talking about intermolecular forces. Sometimes they're called IMFs for short. And I want to be clear about what it is because we've been talking about bonds between atoms, and this is not what we're talking about. So here's a hydrogen and a chlorine. The line that we've been drawing between those two represents a sharing of electrons, and that is a very strong bond compared to the force between entire molecules, which we call an intermolecular force. There are attractions between molecules. They're weak compared to a bond, but they're still there and important. So again, what holds an atom together is a bond, and what holds entire molecules together is called a force, an intermolecular force to be specific. So who cares? How does this help us? Well, intermolecular forces explain a lot about the properties. Like you might say, why do some things melt at this temperature and other things melt at a higher temperature? Why do things boil at different temperatures? Why is it that some liquids you spill on the ground and they evaporate right away and others don't? Why is it that bugs can walk across water? Why does water take so darn long to boil? How come oxygen's a gas at room temperature and other things are a liquid or a solid? Intermolecular forces can help explain all of these things. So it depends on the type of molecule to really help you determine the force that exists. That's why it's good that we've been practicing how to tell if something is polar or nonpolar. And of course, you know, ions are things that have a charge. Okay, so the three types of forces that exist, let's start with the weakest. Dispersion forces, also known as van der Waals forces. Those exist between all molecules. Some molecules also have dipole forces. That's medium strength. And the strongest force between molecules, it's kind of confusing because it has bond in the name. It's called hydrogen bonding forces though. They're so strong, they're almost like a bond. So just for fun, I had some pictures to go along with this during the notes in class. There's strong man for hydrogen bonding. Dipole is the middle. I joked I put my husband for weak, then I changed it to Ed Sheeran. Strongest for hydrogen bonding. Medium, I don't know that she's that medium, but Taylor Swift definitely looks like she doesn't have as much muscle there. Poor Taylor Swift. Alright, let's go into these a little bit more in detail. So, dispersion forces. Like I said, they exist in all molecules. How can this be? Well, even if something is sharing electrons completely, there's still random motion of electrons. So, if you've got an H2 molecule, for example, one hydrogen for a slight moment in time might have a little bit more of the electron cloud on one side of the molecule, giving it a very slight partial negative. The other side then would, for a microsecond or so, have a very slight partial positive. Now, put this adjacent to another H2 molecule, and now they're slightly attracted to each other because of this random motion of electrons. Now, the more electrons you get, even in a molecule that has equal sharing, the stronger this weak force becomes, which is kind of funny to say it that way, but it's true. So, to put it in a different way, bigger molecules tend to have stronger interactions than smaller molecules. Let's look at some examples to help you. Propane is a 3-carbon chain. It boils at -42. Get a bigger molecule that's very similar, it's just 5 carbons longer. Now look at the boiling point. That's because these octane molecules, put them next to each other, and there's more places for them to interact with each other. So they're going to be attracted more to one another than propanes are attracted to other propanes. So it's harder to get these guys apart because you have to break those intermolecular forces in order to boil them. Isomers can have different intermolecular forces too. Check this out. The picture on the left is C5H12, where you've got a carbon in the middle. There's a carbon going up, to the left, to the right, and straight down. The molecule to the right is a 5-carbon chain where all the carbons are in a row. So if you put 2 of this one together on the left, you can imagine they wouldn't have a whole lot of surface area with each other because it's very spherical, versus a long chain and another long chain. They're going to be able to have all these interactions right here. And so the molecule on the right, this isomer, would have stronger intermolecular forces. You can see the boiling point changes. Even though they're both C5H12, the one on the right has a much higher boiling point. Moving into dipole forces. So these are stronger because they are polar molecules. So already one side of the molecule is partially negative, and so in a second molecule, the partial positive side can attract. And so they have a stronger force between them. It's stronger than dispersion, but it's still weaker than hydrogen bonding forces. Hydrogen bonding forces are just super polar molecules that are next to each other, so they're very attracted. So these have to have a hydrogen bonded to an N, an O, or an F. And I always joke, it's like chemistry is fun, F-O-N is the spelling. So water is a great example. Water is very polar. That oxygen is sucking the life out of those hydrogens, so it's got a very partial negative side, and it attracts the very partial positive of another hydrogen on a nearby water molecule, and now you've got a very strong force between these two. So looking at some different interactions here, look at these boiling points. Dispersion forces only, the boiling point's extremely low. That means it's so easy to break forces between H2 molecules with other H2 molecules. Dipoles in the middle, and then this is why water is so darn hard to boil. Okay, so there's just a summary again of the types of intermolecular forces. Okay, so why is water a liquid and oxygen's a gas? Well, we just looked at a picture of H2O molecules attracting to each other. They want to be together, so they're not easy to break apart into a gas. O2 molecules, on the other hand, those O's are sharing equally, so there's dispersion forces only between multiple oxygen molecules. So because they're held together by these weak forces, only due to random electron motion, oxygen's a gas at room temperature. Here's some more properties you can look at. Propane versus ethanol versus, or ethanol versus ethanol. So you can see the boiling points going up as the forces are stronger. Another thing related to this is like dissolves like. What I mean by this is polar molecules tend to dissolve other polar molecules. Nonpolar molecules dissolve nonpolar molecules, and just to be clear, nonpolar molecules will not dissolve in a polar solution. And ionic molecules are very similar to polar molecules in that there's an extreme difference in their charges, so they also dissolve in polar solutions. Let's see, I think we skipped through this and we moved right into some examples. And I want to show you this flowchart that kind of helps you determine which type of intermolecular force is the strongest one present. So first, you draw your molecule. If it's nonpolar, automatically you know that it has the weakest forces between them, so dispersion forces. If something is polar, Then you have to check, does it have an H bonded to an F, an O, or an N? If it does, then it's got hydrogen bonding, the strongest intermolecular forces. If it's still polar but it doesn't have that, it's medium, dipole-dipole. So let's use that to help us to determine what's going on with the intermolecular force between some of these molecules here. So let's start with OF2. This is going to have a bent shape because the oxygen has lone pairs on it. Oxygen's 3.44, fluorine is 3.98. That's a difference of 0.54. That means the fluorine is winning. So the fluorine is pulling electron cloud from the oxygen, leaving the oxygen partially positive and each of these fluorines partially negative. Let's draw a little, I like to draw the force as like a dotted line. Another OF2 molecule that's nearby is going to have an oxygen that's attracted to this negative, partially negatively charged fluorine. So the question is, we know this is a polar molecule because it's an unequal sharing of electrons. What is the force between molecules? Well, it's not dispersion because that's only for nonpolar things. And then we ask, does this have an H bonded to an F, an O, or an N? Well, it doesn't have an H. So that means the force between these is that medium strength one, dipole-dipole. How about HCl? H is 2.1, chlorine's 3.16. That's a difference of 1.06. That means the chlorine is winning and has a partial negative charge. It's stealing hydrogen's electron cloud. So it's definitely polar. And so we have to ask ourselves, does it have an H bonded to an F, an O, or an N? No. So this is another one with the medium forces between them, dipole-dipole. How about carbon dioxide? Oxygen's 3.44, carbon is 2.55. That's a big difference, 0.89. So oxygen's pulling to the right, but there's an oxygen pulling equal and opposite to the left. That's like you walk a block east, you walk a block west. Where'd you end up? Right back where you started. So this is a non-polar molecule. So if there's another carbon dioxide hanging out somewhere nearby, there's only a slight attraction between those two. So we say that has dispersion forces. H2O, we've already seen an example, but it's such an important one. Let's add it in here again. Extremely polar molecule. Hydrogens have partially positive and the oxygens have partially negative charges. So very polar. Does it have an H bonded to an F, an O, or an N? Yes, it does. So the type of force between these molecules would be hydrogen bonding forces. How about CH4? Nothing's winning here. Carbon's 2.55, hydrogen's 2.1. So that means this is non-polar. So if there's another CH4 hanging around nearby, those two are not very attracted to each other. So this would be dispersion forces between those two non-polar molecules. And finally, CH2O. Let's check this out. It is polar because the oxygen is winning. And so another molecule nearby would be attracted to this partially positive end. So since this is polar, but it does not have an H bonded to an F, an O, or an N, it's dipole-dipole forces. Oops, dipole-dipole. A lot of people get confused because they'll look at the formula and they'll say, oh, it's got an H bonded to an O, but not when you draw it out. So be careful there.